I welcome you all in this presentation related with the subject failure analysis and prevention. And now henceforth we will be talking about the failure analysis of the weld joints. Therefore, we will be starting this presentation with the common causes of the weld joint failure. You know, when a particular component made of a metal, its properties are best. But when a component is made by joining the two different members, we have to use either heat or pressure or combination of both these, and that in turn results in the modification in properties of both the base materials of these components, and which in turn affects the mechanical performance, corrosion performance of such kind of the joints. So, it will be the best if the joining can be done without application of heat or pressure, but that is certainly not possible. And therefore, whenever a weld joint is made, there is always some kind of alteration in properties, and that alteration many times lead to the defects as well as modification in structure and properties of the, not just of the weld zone, but also the areas of the base metal which are close to the weld zone. Okay. So, that will be our the zone of focus or area of focus in this presentation. In this presentation, initially we will be talking about the fundamentals of the welding leading to the different kind of the defects and which eventually cause the failure. So, failures due to the defective weld joints or the defects in the weld joints, and the failure of the weld joints also occur when there is no defect. So, that is what we call as a weld joint is not technologically sound. So, technologically unsound weld joints which are sound free means free from defect, but still failures occur due to the deficiency in design, due to the deficiency in the desired set of the properties, or properties have gone have been modified beyond the limits, and that will be leading to the failure of the weld joint during the service. So, the failure of the weld joint due to the deficiency in design, that can be in respect of improper design consideration, means the design property has not been selected for development of the weld joint, or not enough consideration has been given for the degradation in properties of the base material or the weld joint due to the heat or pressure that will be applied during the welding. So, we can say the failure of the weld joint due to the deficiency in design can be due to the two types of the causes. One is lack of proper design property consideration, or lack of enough consideration to the property degradation that will be occurring due to the welding. Okay. So, as I said, the joining of the metals to get the desired size and shape, that needs the heat and pressure, that is what is here, but it will be the best if the two components like A and B are joined without doing anything, but this is not possible. A simple joints like slip gauges also joined together, but not they do not hold each other with the very strong force which will be needed for many engineering applications. So, the next, since this on its own joining is not a workable option, so the next more appropriate option where the joint is developed with very less heat is the brazing and soldering. No melting of the base materials, only the little heating of the components to be joined is done, followed by the melting of the low melting point filler like the brazing metal or the soldering metal, and that will be used for filling this gap. And then the solid state joining, which involves primarily the plastic deformation using controlled application of the pressure force to achieve the interfacial deformation, so that mechanical interlocking, metallurgical bonding across the interface takes place. For this, it is important that the yield strength is low, it is preferred, and the metal system being joined using the solid state joining are having enough ductility. Okay. And also they should be metallurgically compatible, otherwise it will be causing multiple technological issues. So, these are the three processes. One is where nothing is needed, the second one where very limited quantity of the heat is needed, and third one where only force is needed to cause the plastic deformation. Next is where huge amount of the heat is needed to achieve the fusion of the edges of the component to be joined, followed by its solidification leading to the development of the fusion weld joint. Okay. This requires very high amount of the heat, very high net heat input is needed for achieving the fusion of the edges of the components to be joined. There is one more approach that primarily involves the diffusion of the across the interface of the two components to be joined, but this process, like the diffusion bonding or diffusion joining, this also needs a like reasonably high temperature, so that the faster diffusion across the interface can take place in order to develop the joint at the interface. In this case, there is no significant plastic deformation or bulk deformation, there is no melting also of the pink surfaces or of the component being joined. Only the diffusion across the interface takes place, and that helps in facilitating the development of the joint. It is always preferred that if without heat and without pressure, if the joint can be made, that will be the best. Okay. So, heat is preferred only if it is not harmful to the base metallic component which are being joined, like if A and B are being joined. So, application of heat across the between these two members for facilitating the fusion, that heat application is not very harmful. It affects the properties marginally, but not significantly. Many times the degradation in properties is so huge. In those cases, the application of the heat approach for development of the joint is not really very a good idea. So, in that case, the pressure based weldings are used or deformation based processes are used. So, heat is used if it is not harmful, and pressure is preferred if heat is not desirable. Okay. So, sometimes we use a combination of the heat and pressure both in order to facilitate the joining of the difficult to weld metals. Okay. So, we will be primarily focusing on the fusion welding, which requires a huge amount of heat. So, even then also we try to develop the joint with the minimum possible heat, so that the adverse effect of the heat application on the joint characteristics is minimized. Okay. And that is why we will see that not very less amount of the heat or not very high amount of the heat will be a favorable situation, because very less amount of the heat leads to the development of the defective weld joints, while the large amount of the heat if used for developing the weld joint, then it will be compromising the base metal properties and also weld metal properties significantly. Okay. So, we need to optimize the amount of heat that is being supplied. Just to understand the things in better way, like say this is a component, okay, these are the two components A and B which are being joined. Okay. So, each one will have, say, assuming that they are made the same metal. So, A and B, these are two different components, but the metal is same. So, it will have certain set of the mechanical, physical, chemical and metallurgical properties. Okay. So, what happens when we apply heat for facilitating the fusion of the edges of the component through the suitable heat source, which may be laser beam, which may be plasma, which may be gas, or which may be arc also. So, the heat application, what it does, a part of the heat is dissipated to the underlying base metal due to the thermal conductivity, and that in turn modifies the properties of the base metal to some extent. So, this zone where property modification is taking place due to the heat application is called heat affected zone. This zone will have a set of properties which are not there even in the base metal, means properties will get modified, properties will get altered. Many times these alterations are not acceptable or not desirable. Okay. So, this is one aspect. Second aspect means, so there is a zone formation which is affected by heat called heat affected zone, having the set of metallurgical properties, mechanical properties, or even the chemical properties such that they compromise with the joint performance. Okay. The another aspect is like a weld metal zone formation, weld zone formation. So, in the weld zone formation, what we have this zone. Okay. What is this? This zone can be developed either through the autogeneous approach, where means the two components subjected to the application of heat and direct fusion followed by solidification, leading to the autogeneous welding. Okay. But if the thickness is great, then we have to prepare a groove, and this groove is to be filled in by the molten metal through the number of passes. Okay. So, this weld metal can be of the same metal or can be of the different metal. Okay. So, when the fusion welding allows the use of the filler, then we can choose the suitable compatible filler. But in case of autogeneous welding, there is no filler, only the direct ends are fused to develop the weld joint. Now, this filler is a very good feature when the consumable electrode is used, means this filler can be chosen as per our convenience. It can be of very low yield strength as per requirement, or it can be of very high yield strength, can be of the low toughness, or it can be of very high toughness. It can be low corrosion resistance, or it can be high corrosion resistance. So, as per the need of the application, we can choose the suitable filler metal, but when autogeneous weld is made, then there is no choice. We do not use any filler, and whatever properties we get in the weld joint, that is corresponding to the metallurgical transformation that will be occurring in the weld zone during the cooling from the, you can say, after the solidification, cooling from a high temperature to the room temperature. So, lot of solid state transformations will be occurring, and that may be leading to the favorable or also unfavorable characteristics, but at the most what we can have the property similar to the base metal. Okay. There is no possibility of having the different set of properties like what we had in this case where we use the filler metal from outside. So, bringing in the filler metal with using suitable kind of the electrode is a very good feature of the consumable arc welding processes, which feature is not available in the autogeneous welding. Autogeneous welding is particularly used for joining of thin sheets, okay, like using laser welding or the TIG welding. Now, once the weld joint is made, what we have seen is, like say this is the component A and B, and where the weld joint has been made like this. Okay. In vicinity we have the heat affected zone HAZ. Now, when the joint is subjected to the external loading, what we can have, like say the component A base metal and the base metal B, okay, the two members of the same base metal, say what happens, each one will have its own heat affected zone, and in between there is a weld metal. So, when the weld zone is weak due to any reason, say there are defects or inclusions, porosity, defects in form of inclusions, porosity, cracks, or the yield strength of the weld metal is low. Base metal is strong, but yield strength or the mechanical properties of the weld metal are poor. In that case, failure certainly be occurring from the weld metal. So, this will be indicating that our weld metal is poor in terms of the properties. Okay. It is also possible that the degradation, the weld metal is quite strong, but heat affected zone properties have been compromised to such an extent that the failure takes place from the heat affected zone. In that case, our approach will be different. In the first case, what we can use the more appropriate weld metal, the more appropriate consumable for develop filler or electrode to develop the weld joint. But in the second case, here we do not have anything in our hand except that reducing the severity of effect of heat, that is in the heat affected zone. Okay. So, if the failure is occurring from the heat affected zone, then it needs a different approach to improve the joint performance. Okay. It may be in form of like use of high power density. So, the heat input is reduced, heat affected zone formation is minimized, and its set related adverse effects are also minimized. Okay. Another thing is that very controlled forced cooling, superficial cooling can be applied in zones, in certain zones selectively, so that adverse effects related with the heat can be minimized in the heat affected zone. If the weld metal is good, not much the properties of the heat affected zone has been compromised or the properties have got enhanced, then the weak zone may be in the base metal. So, the failure from the base metal will be taking place. In this case, what will we notice, that our heat affected zone and the weld zone is strong, but the base metal is weak. Okay. So, as per the failure location, we have to develop the strategy for enhancing the performance of the weld joint using the suitable filler or electrode, or minimizing the adverse effect of the heat in the heat affected zone, or if everything is fine, then the base metal will fail. When the failure from the base metal occurs, means our operation or our objective of developing a weld joint has been successful, it is the base metal which is failing. So, we say that our joint efficiency in that case is greater than 100%. Why? Because in that case this entire heat affected or weld zone will not be failing, but it will be failing from the base metal. Okay. What alternatively we can do is this: select a suitable small size sample from the weld zone and test its properties, say they are 700 MPa, and take the sample from the base metal and test its properties, and say these properties are like ultimate strength of the base metal is 500, then ratio of the the weld metal properties 700 divided by the base metal properties of 500, this will give you the joint efficiency. Weld metal is stronger than the base metal, will give you the efficiency greater than 100%. And that is why in such cases, that is the case this, where the heat affected zone is strong, weld metal is strong. So, the failure is taking place from the base metal. Okay. So, in all those cases where the failure occurs from the base metal indicates that joint efficiency is greater than 100%. Okay. So, what is needed as far as the sound development of the joint is concerned is minimize the effect of the effect of the heat that is being supplied by reducing the HZ. Okay. Protect the weld metal properly so that there is no porosity inclusions, okay, and fine grain structure is achieved. So, when the heat input and proper protection to the weld pool is applied, very narrow heat affected zone weld metal with the free from the porosity and inclusions is realized, and the weld metal having the fine grain structure. These are the things. So, low heat input and good weld pool protection are actually are the key for developing the sound weld joint, and which will offer greater resistance to the failure. Apart from that, there are many metallurgical failures or technological other kind of the aspects, like solid state transformations in the weld joints sometimes occur in such a way that they degrade the toughness, induce the residual stress, incorporate the hydrogen concentrations, and promote the cold cracking in the weld zone. So, these kind of the things need more careful attention regarding the choice of preheat, choice of filler, post weld heat treatment in order to control their adverse effect on the weld joint and the related failure tendency. The properties which are actually very important for developing the sound weld joints which are free from the defect include like the melting temperature, thermal conductivity, thermal expansion coefficient, and solidification temperature range. When the solidification temperature range is high, solidification cracking tendency is also high. Okay. When the expansion coefficient is high, residual stresses are high. When the thermal conductivity is high, we need very high heat input in order to facilitate the fusion weld joint, and likewise when the melting temperature is high, it makes the fusion of the fin surfaces difficult. We need more intense heat. Okay. Likewise, the metallurgical aspects related to the base metal also affect the soundness of weld joint and the joint characteristics like solid state, phase transformation, solubility, strengthening mechanisms. So, their metals strengthened by certain mechanisms are more affected by the welding heat as compared to those of others. About this we will be talking little later. And the mechanical properties that are significantly affected are like hardness, ductility, and yield strength. Chemical properties like composition of course is of great importance in determining the ease of welding and the affinity of the metal with the gases. Like if the metal is having the greater affinity to the gases in form of high solubility, gases getting dissolved, or they are reacting high reactivity, both these create problem in form of porosity and inclusions. If the gas is having the high metal is having high affinity with the gases, the porosity and the inclusions are really very much problematic, like in case of the aluminum. Okay. In case of the steel, composition is of the great importance because it directly affects the carbon equivalent, chromium and nickel equivalents, which in turn affects the phases that will be developed in the heat affected zone and in the weld zone after the welding, and these aspects significantly affect the weld joint properties. Say in this case here, say the two metals being joined without doing anything, A and B, and joint is being developed nicely without any problem. So, there is no change, no alteration in properties. When the soldering is applied, little heat is applied to the fang surfaces, and only melting of the filler, low melting point filler is done. And when the fusion is used, then we get the very wide weld zone and the heat affected zone in the two sides, that will be compromising with the joint properties, and that in turn will leads to the. So, this is our case of the fusion welding, where two heat affected zones on the two sides and one weld zone is formed, and that will be leading to the compromise in the properties of the base metal. That compromise in the heat affected zone may appear in form of, like, it can lead to the hardening, it can lead to the softening or embrittlement. Okay, development of residual stresses, which will be leading to the distortion, cracking and inclusion. So, when the welding is done, an appropriate combination of the welding conditions can lead to the hardening and embrittlement, softening of the heat affected zone, development of the residual stresses, which will be degrading the mechanical performance, and cracking, inclusions and porosity. So, these are the issues related with the fusion welding. So, if you want to see the performance of the weld joint in summarily, then joint has to be sound. Okay. Weld microstructure and heat structure of the weld metal and heat affected zone must be favorable. Okay. The weld zone and the heat affected zone must be narrow. Microstructure of the weld and heat affected zone must be favorable, which in turn will be leading to the desired set of the mechanical properties. And in addition to that, residual stresses need to be minimized, so that adverse effect of these on the joint performance during the service can be minimized. Okay. This in turn depends on what? The weld metal properties are governed by the choice of the filler in case when the consumable arc welding process is used, but heat affected zone, not much can be done with the heat affected zone except that reducing the heat input, and for that, as I said, use of the high power density welding processes is preferred. Okay. So, the weld metal properties, especially the mechanical and corrosion properties, these depend on what? Composition of the weld metal, weld thermal cycle being imposed, and of course, soundness. So, if the weld joint is free from the porosity, inclusions and cracks, even then there can be issues in terms of the poor mechanical properties, poor corrosion performance if the composition of the weld metal is not proper, or inappropriate weld thermal cycle has been imposed, because weld thermal cycle determines primarily the cooling rate, and the cooling rate affects a lot of compositional structural issues, structural aspects. So, weld metal properties are also affected by the protection of the weld metal and the heat input. So, all these, the mechanical properties and corrosion properties, corrosion resistance of the weld joint will depend upon these two bigger factors, heat input and the protection. Okay. Because protection determines the soundness, heat input determines the cooling rate or the weld thermal cycle for a given composition of the weld metal, that will be affecting the microstructure, and which in turn will be affecting the mechanical properties. This is the sequence. Protection is needed particularly to make the sound weld joint free from porosity and inclusions. Heat input is needed for optimum melting without excessive heat, so that it affects the weld thermal cycle, and for a given weld thermal cycle and for a given weld metal composition, we get a proper microstructure or particular kind of microstructure, which will dictate the mechanical properties. Okay. So, it is required that the heat input is optimum. Okay. When the heat input is low, very low, then it leads to the weld discontinuities and stress concentration, stress ratios in terms of the, like, the lack of penetration, lack of fusion and underfilled sections. So, that will be decreasing the joint performance. On the other hand, when the heat input is too high, then it will be leading to the very coarse grained structure, very wide heat affected zone, and that in turn and very high residual stresses also. So, these factors in turn will be decreasing the joint performance. So, neither too low heat or too high heat will be favorable. We need to optimize, or we need to, through the proper welding procedure, we need to establish the optimum amount of heat, so that the joint is sound and it is having the desired set of the properties. The performance of the weld joint can be easily related with the heat input, and why? Because heat input used for the welding purpose directly affects the cooling rate basically. So, cooling rate is found inversely proportional to the heat input. Higher the heat input, lower the cooling rate. Okay. Low heat, then the cooling rate will be high, and cooling rate is extremely important. Why? Because heat input is one thing that affects the cooling rate, and apart from the heat input, of course, the thermal conductivity and the thickness of the component being joined are the other two aspects that will be affecting the cooling rate. Cooling rate is extremely important. Why? Because it affects the grain size. Okay. A higher cooling rate, the finer the grain size. Okay. Fine grain size is achieved through the high CR. Okay. And high CR means the less segregation tendency, because the weld metal does not get enough time for the segregation, rejection, etc. Okay. And likewise, when the grain structure is fine, then we get the improved mechanical properties. So, these are the three favorable things which will be realized, but when the cooling rate is high, our solidification time is very less. So, when the solidification time is less, then there is a tendency of the entrapment of the gases, entrapment of the inclusions. So, there is a possibility like that the inclusions and the porosity formation tendency is increased. Okay. If the cooling rate is slow, then the things will be rejected slowly, the gases will have enough time, inclusion will have enough time to come up to the surface and float over the surface. So, but that does not happen in welding, because the solidification time is usually very low. So, the cooling rate directly affects the solidification rate, solidification time, and eventually also the solid state transformation. Solid state transformation is extremely important in case of the transformation hardenable metal welding like steels, copper, titanium, etc. Solidification rate of the weld pool determines the grain size of the weld metal, grain size in the weld metal, and the inclusion and gas entrapment tendency, mechanical properties, and alloy segregation. Okay. So, it is important that the H net or the net heat input is optimized. There is another way also of adjusting the cooling rate for a given heat input, for given thermal conductivity, given section thickness, is use of preheat. So, use of preheat actually reduces the cooling rate, and that in turn helps in realizing number of things which are otherwise difficult, okay, like reduced embrittlement tendency, reduced hardening, and reduced residual stresses, so reduced cracking tendency. So, depending upon the metal system, suitable preheat and a heat input is optimized and established for developing the sound weld joint. I was saying like how to reduce the heat input. To reduce the heat input, the best way is use the high power density processes. So, the different welding processor of the different power densities like gas welding around 100 to 1000, okay, manual arc welding process around 10,000 watt per centimeter square. Then for MIG, it is like say 10 to the power 5, for plasma 10 to the power 6, for the electron beam say 10 to the power 8, or more than 10 to the power 8 for the laser welding. Increasing power density means lot of energy is localized and applied over a small area, therefore, it needs very less time for facilitating the fusion and developing the weld joint. So, high power density facilitates the reduced heat input, net heat input required for the welding purpose. Okay. When the net heat input is reduced, okay, reduction in net heat input, basically this causes the reduction in the heat affected zone, residual stresses, distortion tendency, okay, all these undesirable effect of the high heat input are minimized. So, this diagram what it shows that like when the heat power density like say PD is high, it takes very less time to achieve the molten state, and the welding is done quickly, and therefore, the heat dissipated to the underlying base metal is also reduced, and that in turn reduces the heat affected zone. But when the power density used is less, in that case it takes long time to deliver the desired amount of heat for fusion, and therefore, it will be taking very long time, and in meantime lot of heat will also be dissipated to the underlying base metal, leading to the wider heat affected zone, And so, the low power density needs the high heat input, okay, high H net, while the high power density needs less heat input. Say this is the extra amount of heat that we need to supply for when using the low heat input low power density processes. Okay. So, this is a schematic diagram which is showing that the power density of the welding process and how does it affect. So, the power increasing power density of the heat source and the heat input to the workpiece. So, when we are working with the low power density, say for gas welding, a lot of heat is to be supplied, that increases the thermal damage, wide heat affected zone, and the greater degradation in the base metal properties. For arc welding processes having the little higher power density, so this kind of the thermal damage is minimized. But when we are working with the high power density process like electron beam and the laser beam, our penetration depth is increased, welding speed is increased, weld quality is enhanced, but the equipment cost is high. Okay, so now we will see that a certain kind of the metal systems and the way by which they are affected by the heat. So, here say these are the 6 common metal strengthening mechanisms: work hardening, grain refinement, dispersion hardening, precipitation hardening, transformation hardening, and solid solution strengthening. So, if we see when the heat is applied for the welding purpose, the metals strengthened by dispersion hardening and solid solution strengthening are not much affected by the heat. But if the metal is strengthened by work hardening, grain refinement, precipitation hardening and transformation hardening, then these get affected by the heat application significantly. Okay. So, depending upon the kind of metal which is being subjected to the welding, using the fusion welding approach by applying the heat for melting the fine surface of the component, and they will certainly be affected by the heat significantly. Now, I will summarize this presentation. Basically, in this presentation I have talked about the fundamentals related with the fusion welding, and that will be leading to the various kind of the defects and the issues that can lead to the failure of the weld joint. Thank you for your attention.